wanted to say what I'm going to do, and I'll do the same thing tomorrow night, hopefully a little smoother, because we had some other things going on. And apparently I can't use my own computer. I've got to use the UBarU one. Typically what I'll do is I'll review some of the things we did the night before, some of the highlights, and then I will add new things to it. So like for instance, tonight, I'm going to add some more about planets, but also some things came up about some of the things we did last night. So last night, the main thing we talked about in the beginning was the comet Neowise. So let's look at what that is. See the slide here, and I think John had shown you this a little bit earlier too, but John Phelps, he had it in his presentation. And he took this picture, and I had said this was Donnie, but he says, no, that's me. So he said he kept taking pictures. But one of the things about Neowise, you know, like I told you last night, the comet was named for the satellite Neowise. Now, Neowise originally wasn't called that. It went up, you know, it was a, it was launched as a satellite telescope that was going to map the entire sky in infrared. So that was its job. So make a complete map of the entire sky, you know, over 360 and everywhere, all dimensions, so that you could see all the sky in infrared. It finished that around 2012. So they were about to decommission it, didn't know what to do with it, but then people became getting more and more concerned about near-Earth objects. And they said, well, we can reprogram this thing and it can now become, let's look for near-Earth objects. Obviously, these are rocks and asteroids, any kind of thing that shows up in the space. And the problem with near-Earth objects is that there's a chance they will strike the Earth. Now, most of you probably have heard about what happened to the dinosaurs 65 million years ago. Well, that was an asteroid that was, I forget about how big it was, but it wasn't that big. 6 miles, 5 or 6 miles. So, and it put a cloud around the Earth that took years to subside, and by that time the dinosaurs died. Well, and the little mammals were in better shape, so that's where we came from. At any rate, they decided we need to start mapping these things and detect them as early as possible. So if the one does show up this problematic, we can deflect it, hopefully. So, or blow it up or whatever. But people say, well, you don't want to blow them up, then you get a rain of small ones. I think that's probably better than one big one. The thing that hit in Russia several years ago was about the size of a small car. They say they'd like to say the size of a Volkswagen. And that raised quite a bit of havoc just for that thing. So when you start getting bigger, something way up in hundreds of feet wide, it can take a city out. You get to be 5 or 6 miles, it could, it's extinction type thing. So the idea was that now it does that. So as part of its new mission to search for near-Earth objects, it found this comet. Back in the so they decided, well, we don't name it after people who discover them, we'll name it after the satellite that discovered it. So it did a good thing. So I'm not really sure what they'll do if they have another one. So there you are. Now we had about 4 pictures of the comet last night. This was the one through the telescope. The others all the best pictures we got were with just nightscaping, just from a camera on a tripod. And the very best one, I think, was the one that John took from his house in Austin. But this was one of the ones we took through the plane wave. We overexposed it a bit. We messed around with it enough at this point. We had some other photographs we thought showed the comet better, but you can see the gas. This shows the coma. The actual comet itself is, let's see, I was trying to think about how big it is. This comet was about 3 miles wide, its core. And to put that in perspective, I think if you remember, we said that the Halley's Comet, which is a short-term comet, comes every 76 years, is around 10 miles in diameter. So this thing is about, Halley's is about 3 times as wide as this. But the coma is much bigger than that, much bigger than the diameter of the Earth, because that's the gases that are melted. And the color will determine on what the elements are in there. I don't know what's blue-green. So anyway, that's what that was. Then I showed you a picture of Jupiter last night. Now, it turns out in this photograph, Io is behind the planet. So you have Callisto way out here, You have Ganymede here. Ganymede is the largest moon. In fact, Ganymede is the largest moon in the whole solar system. So over 3,200 miles in diameter. This is Europa, which is, I think, I got the question last night. It's 1,960 miles in diameter, which is slightly smaller than our moon. Callisto is just under 3,000 miles in diameter. It's like 2,996 or something. And Io, which you don't see, or Io, either one, is about 2,200 and plus. So those are the four moons, but like I said, those are the four Galilean moons. You don't see Io in this photograph. Tonight, when you come up to the observatory, you will see again the planets. We'll start out with Jupiter because it's higher, followed by Saturn. You did not see Saturn last night. Oh, excuse me, I didn't show you Saturn in the show. You saw Saturn up at the observatory. So with that, this is the photograph we got of Saturn. So you did not, like I said, what you will see here, there are three major rings around Saturn. Actually, lots of little ones, but there's the famous Cassini divides between, the biggest one is between what they call the A ring and the B ring. There's actually another one in here that's a little dimmer. If we had a little bit better resolution, you'd be able to see another divide there. But you do see the main divide between the A and B rings. So I think it's a pretty good photograph. You can see some of the banding on the planet's surface. You know, as far as Saturn, Saturn is about 75,000 miles in diameter. So it's, you know, it's a little more than 8 times the diameter of the Earth. And it's interesting thing about Saturn, several interesting things. Of course, the rings are the most interesting thing. But one of the other things that's interesting about it is its density is 0.7. Now, water is 1.0. So this thing is, the overall density of this planet is less than water. So, you know, if you were to get on it, you could actually, the things could float. But they don't say that this is very much like Jupiter's ceiling, because they are very, very similar in makeup. The surface which you see here, is gas. So if you were somehow to step on it, you'd start immediately going through gas. It's just, and then it's hydrogen gas. Just below that, you have liquid hydrogen. And then below that, you have a shell of what they call metallic hydrogen. And then you get to a rocky core. But that's the same way that Jupiter is built. So they're very, very similar. The rings, the diameter across these rings is around 170, to make sure I tell you right, 170,000 miles. Okay, 170,000 miles across, but they're less than 2 miles thick. So they're very, very thin. Now, you know, some people say, well, where did these come from? And the two leading theories of where the rings came from, one, which seems to be more popular now, but I got to check some of the things. You know, you read the astronomy books and you look up and you'll get something, and one 2 years later says something slightly different. So, but the one that they seem to be more favorable to now is that the rings are the remnants of a moon that got too close to the planet, and the gravity broke it up. So the other thing was that it was a debris that never, when the planet was being formed, it was, you know, it started out as a swirling set of gas. Well, when it started making particles, these never coalesced to make a moon. So you can have one or the other. You know, those are the two best ones. But the main thing is it's gorgeous. You know, the thing about seeing Saturn for the first time through a relatively large telescope is awesome. You know, I write stuff every now and then, and a lot of little stories. And one of the things that I did write was called Saturn and Kelemy Crater. When I was a sophomore in college, I had two, you know, life-changing events. One was I went to the observatory with a friend of mine was getting, he was one of the last people to get a minor in astronomy. He was very much a Renaissance type guy. He was majoring in English, but getting a minor in astronomy, and was an incredible art. He became a full professor at Princeton in mobile art, because he would always make these elaborate contraptions, mainly for homecoming decorations. But he liked it. But he would take me over to the observatory, and it was pretty open back then. The school was not that big, but we had a 15-inch refractor. It was made in Ireland by the Grubbs and family. And like these older telescopes, in order to get rid of the chromatic aberration, you had to have a very, very long ratio, F ratio. Otherwise, you'd see, color bands around whatever you looked at. So the older ones the best ones were doublets. It means we had two compart lenses. And the reason you have two kinds of glass is that they would bend the light slightly different. Hopefully the second one would correct some of what the first one was causing. Well, and then if you made the focal ratio very long, that even reduced it further. So this thing was, when I say it's an F15, that means it was 15 times longer than its diameter. Well, if the lens was 15 inches across, it was 225 inches long. And then you had little stuff on either end, like with the eyepiece and the dew shield and that sort. The thing was over 20 feet long. And it was on a massive pier. It had this is way before anything that you might have thought of it by a thing like go-to telescopes, because it was built in 1893. There were these enormous brass setting circles where, as a graduate student, my job, later on I got a job and worked at the observatory, I'd have to go over there and set it up for the night's viewing for the astronomy class. And so I'd have to look up in a book what they were going to look at. And I'd have to dial in the right ascension and latitude, and right ascension and declination on these big circles. And that amounts to the same as latitude and longitude. So anyway, I saw this thing. And I was just absolutely blown away my sophomore year. Well, that same year, I was beginning to get serious about singing. And it was determined that I was a tenor, with no doubt. So I went and checked out all the recordings in the music library of tenors and started listening to them. And people had, a year before, tried to get me to go to Memphis to see the Metropolitan Opera. I said, oh no, that's long hair stuff. I don't want to do that. So I started listening to records, and the records I liked, I put over here, and I didn't like, put over there. And then all of a sudden, to my surprise, all the ones I liked were opera singers, operatic tenors. But the one record that absolutely blew me away was a recording of U.C. Björling, the famous Swedish tenor, singing Kella Mi Kreda from The Girl of the Golden West. And I was just the same way as I was when I saw Saturn. So I even kept borrowed that recording in my dormitory room for about a month before I took it back to the library. But later on, I was able to get a CD with that. But anyway, I said those two things occurred to me in the same year. But it was kind of, when I watch kids that come up here and they look at Saturn for the first time, they're wow, they just taken back. So one of the star parties that we had here, when I saw those kids, I went home and wrote that piece because I said, I remember that, all these years later. Anyway, Saturn is something to behold. Let's see if there's anything I should have told you besides stories about Cassini vision. It has lots of moons too. We talked about Jupiter having 39 moons, and of course the 4 Galilean moons we just reviewed again. Well, Saturn has about 30. They're not sure if that's all, because it can have some real little things that are moons, but it has 4 fairly large ones. Titan is the largest of its 4. And Titan is the second largest moon in the solar system. So it's over 3,000 miles in diameter. It's much bigger than our moon, almost as big as Jupiter's Ganymede. And then it's got the others that are less spectacular. You probably haven't heard of them that much. Iapetus, and then Enceladus is one we have heard of. That's another one that they think might be potential for life. Yes. Why does it have a moon? Why does it have a moon? Well, its gravity captures something. In other words, something gets close to it. And the thing is, typically, a lot of these things happen, the moons occur when the planets are forming. And so you start out with a mass of gas that's swirling. The central thing makes a core, some left over makes little pieces, and that becomes a moon. So that's how a lot of them are done. Other moons are captured. Something comes passing by and it says, I like that. So the gravity pulls it in. But the reason it has it is because of gravity. And typically speaking, the difference in the mass of the home planet, the mother planet, or whatever you want to call it, is many times that of the moon. And not always. Pluto is an exception, which is no longer a planet, by the way. But still, if you look at our moon, Its mass is about 1% the mass of the Earth. And if that's about the same sort of thing when you look at these others up here, it's the mass of the moon is very much less. So most of them probably formed when the planets were formed. Ma'am. Oh no, they're outside that. Like we said, what happened to that ring, one of the leading theories of what the rings are, is that a moon got too close and was pulled apart by the gravity. So the moons are all outside there. You're not seeing any of those. You don't have them, it doesn't. First place, Saturn is almost twice as far away as Jupiter. And it's not quite as big. Jupiter is 11 times the diameter of the Earth. It's 33,000 miles in diameter. And it's half as far away as, well, a little over half as far away as Saturn. So that matters. And so the fact is that you stick these things further away, they're much less bright. And, most of these things are smaller. So you can see Titan typically with good magnification and a good telescope. You can see Titan. We might see that tonight. Yeah. Yeah, right over the right. You probably see it, but you most likely will not see the others. Okay, they're not in this picture at all. Now, the Earth's about 3,000 miles in diameter? No, the Earth's about 8,000 miles. It's just under that. It's like 7, 9 something. In other words, just right. No, our moon is 2160, I think, and ours is about. And our planet is right at 8,000 miles, which is about the same as Venus. Okay. Now, where was I going to? All right. Now here is the. Was that 5? Okay. Yeah. This always helps. Okay, this is a star cluster, or at least part of it. You can't see the whole thing, but this is M7. It's Messier number 7. It's an open star cluster that's in the constellation Scorpius. Now, once again, all of these photographs you see here that were taken through the telescope, we was using my Canon EOS 77D camera. So, and this was a bit of a time exposure. The stars are fairly well defined here. They look like round dots. Now, that's another thing to think about a star. When you take a photograph of a star, it never gets bigger. It gets brighter, because they are all, even the closest star to us is so far away that you would never be magnified enough to see the actual disk. So that's one of the reasons why when we're looking at deep sky things, we don't worry about the magnification. We care about magnification when we want to separate stars that are close together or something like that. But we don't care about it for looking at the size of the individual stars, because you'll never do that. These stars here were brighter to start with. So then in the time exposure, you see that they flare out like this. If we'd played with this enough, if this had been our main thing, we would have probably ended up with some things where we would have toned down, we wanted to show some of the dimmer stars. So we'd have probably toned these things down a bit. But anyway, what can I tell you about that? I think, let me see, I did some notes about how big that is. An open, you saw the globular cluster last night that we took pictures of. Well, the stars are much closer together in that, and they're much older. And this one has about 80 stars in it, this cluster. Now, you don't see 80 stars, but that's about when they are. The complete field across this cluster is about 20 light years. Okay, that's that's much more open than a globular cluster, but still a lot further. That's a lot closer together than the stars that we see around us. The very nearest star to us is Proxima Centauri. You've heard of Alpha Centauri. Well, Proxima Centauri is a little bit closer. Both of them in the constellation Centaurus. That's a little over 4 light years away. And so you start looking if you look 20 light years out, you're not going to find 80 stars. So that's, so anyway, they're relatively close together. It's young, it's a relatively young cluster as opposed to the globulars. So they will eventually, that some of these stars were forming in the same field, and then they will drift apart later. What else can I tell you about it? Oh, how far away it is. It's about 800 light years from us. about 800 light years from us, that cluster. Now, remember how far away we were talking about the globulars? You saw M13 last night, it was 25,000 light years away. And we mentioned, and I mentioned, I think you saw another one up there that was even further away. You saw one that was closer when you were at the observatory. The one that's the biggest that we see in this, that we see from this planet, is called Omega Centauri, and that's in this, it's mainly the southern hemisphere. We can see it briefly in the summertime from here, but where we are located, it's very, very low in the southern sky, and so we only had one shot to get a picture of it, and it clouded over, so we did not get a picture. We had really hoped to. In June, we would have been able to do it, but we could not. Okay, so. Okay, this is a little bit, another picture of M7, just a little bit different angle. But we didn't have the whole thing in the field. A lot of these star clusters are going to look better through a wide field telescope, you know, what they call fast telescope, one with a shorter focal ratio, because it gives you a wider field rather than a more narrow. And the Celestron, the plane wave, is an F8, which is a lot shorter than the F15 I told you about at the university. But nonetheless, it's not going to have as wide a field. So, and these star clusters, when they are spread out a bit. So, and these open ones, a pair of binoculars will usually show you a picture, or at least in the Dobsonian, being it's like an F5 or F6 up there, it'll be good for this. But we were taking photographs here, so that's a piece of it. But it's, the data is all the same. It's still 800 light years away and all the other stuff. All right, now. Here is a double star cluster. This is the famous one in the constellation Perseus. Some of you may have seen a bit of the tail end of the Perseus, the Perseids meteor shower last night. Okay, so this is in the same constellation. Okay, so you see like there's two groups of stars here and here. They are actually fairly close together in astronomical terms. They're about 8, you can't see all of them because they're pretty far away. This double cluster, those two clusters are about 7,500 light years away. That's a long way. And it's about 300 stars in each cluster. But we only see, you don't see anything like that. But they are open clusters. They're not as tightly packed as a globular. And it's a long way. So I don't know if we will catch that tonight or not.
Naked eye.
Yeah.
I was blown away.
What?
I haven't seen the double cluster
Yeah.
naked eye in a long
So you saw it.
Saw it.
All right.
Naked eye, I guess it was about 1:15.
Good. And tonight's supposed to be pretty clear as well. So you can look. Yeah. I tell you what, after all day yesterday and all the the conduction, I mean, telling everybody what we were seeing up there, it's a little bit tiring. So I was ready to turn in when we finished at the observatory. It's a little after 11. Sometimes, like I said, when John and I were taking these pictures, if you notice the date, you don't see the date, maybe you. This was taken on July the 24th. Now I was showing you the others of Jupiter and Saturn were taken on July the 23rd. Guess what? This was after midnight. This was actually more like 4 in the morning, because what we did was we went up there and we took images up till about midnight or a little after. Then we went down and grabbed a 3-hour nap, and just so we were both, we were getting fumble fisted up there. And Donnie left a lot earlier, so we went down and grabbed a little nap, and went back up there by 4, and mainly to catch Mars. But guess what? A cloud bank rolled in the east, and so all Mars was an orange disk. We couldn't see any features, and we took pictures, but we didn't show any of them to you because you can't see anything of it. It's just a little round, just a little orange ball, because the clouds were so thick. So,
Stay up until 12:30?
yeah.
That road right up there?
Yeah.
Mars comes
Right up, yeah, right. It's just rising now, after midnight sometime. but it'll be high enough. You know, we talked about the ecliptic, where that's the path that the sun takes during the day across the sky. Well, it turns out that the planets are most of the planets, nearly all, yeah, all of them, the Pluto's not anymore. Anyway, we talk about the planets are in virtually the same, pretty near the same plane as the sun. So they will follow the same path that the sun does. So you can, and of course, in the summertime, we are tilted toward the sun, tilted that way. So it's higher. In the winter, it's lower. But so that's why I say that we can see Omega Centauri in June, because that's the high point of the you know, of the ecliptic. And so it's high enough to actually, you can see it even after that, but it's high enough to see and photograph. Sir?
This may be really basic, but the North Star,
Yes.
Polaris, is the focal point around which the whole sky
Well,
rotates, right?
well, it appears that, but it's not exactly the North Pole. It's close enough. It's within a half a degree.
Is it counterclockwise or
No,
clockwise?
it's what happens is you have it's circumpolar. So I'm just trying to think about how it looks. I never even thought about that.
You mentioned
which
that
one?
Mars was rising, and I was wondering whether
Well, no, it appears to. I think it's go this way, but I really don't. You know, sometimes people ask me a question, I haven't thought about it. I just look at it. But what happens is you will find that a number of constellations, like the Big Dipper, which is actually an asterism, the constellations were some major. But what it does, it will appear to just go across the sky. The end of the Dipper, the two pointed stars, will always point to the North Star. It's about 5 times the gap between those two. So you can tell that, but you will, throughout the year, you will see that the Big Dipper go right around, like the pointed stars always point to it, but it'll go all the way around. And then the handle is like, so.
we'll look at it tonight.
Yeah, we can take a look at it and see what you see. But anyway, this is one of the famous clusters. We should be able to see that certainly with a telescope. Now let's see what I have next. All right, I showed some of you all this last night, and we'll do more of this tomorrow night, because I'm going to do more double stars tomorrow. This is Alberia, and it's probably the most famous and it's also the prettiest double star you'll see. A double star is a star, when you look at it with your naked eye, it looks like one star. But when you look through a telescope, you find, aha, it's not one, it's more than one. Two is a double, but it actually could be like 3 or 4. But anyway, this is a famous double. And there was a long time argument about whether it was a visual double, which they may have been far apart, actually in space. But when you look at them, they just along the same line of sight. So the question was it that, or was it a binary? A binary star is one where the 2 stars are revolving around a common point. So I looked this up myself a couple of times before tonight, and I've talked about it. And more recent thinking says it's not a binary. It turns out that they're both out in the same region. They're both between 300 and 400 light years away. But being a light year apart, it'd be quite a ways. So the feeling is, of course, the orange one is bigger. It's a little closer. It's got a magnitude of about 3. It's the 3rd magnitude. And the blue star has got a magnitude of about 5. So the bigger number means the dimmer it is. So but the feeling is that, the argument was that they are actually binaries that they're pretty far apart. It just takes a long time for them to make an orbit around each other. And I read something that was written in 2018 that said the argument is finally settled. It's a visual double. So now it is. We'll say that. Anyway, it's like I said, it's really pretty. And where is this? Well, if you look up in the sky, this is the head of the constellation Cygnus, the Swan. And Cygnus is in the, another way to find that is to look at, if you look in the summer sky, there's a thing called the summer triangle. Vega, which is one of the brightest stars you'll see, is here. And you have Altair there and Deneb here. Deneb is the brightest star in the constellation Cygnus, but it's the tail. That's what the word Deneb means. It means a tail. So Alberio is up at the head, but it's not as bright as Deneb. Now, Also, another name for Cygnus is the Northern Cross, because it looks like a cross. It actually, in the mythology, the cross, that's his wings, the tail and the head's along a long neck and the head. But you also see a cross there. Anyway, it's a very pretty thing. If you didn't see it last night, we'll show it again probably tonight. Okay. Now, we have a couple of nightscape shots here. I don't know if I showed you all this one last night. I don't think I did. Here you have Jupiter and Saturn right here. Jupiter and Saturn, see those? And this is the Milky Way. This is really Sagittarius area here. Scorpio is just, the stinger of Scorpio goes right there. So anyway, we captured both of them looking back. I was trying to see if, I asked John to see if we could kind of catch one of the star clusters over here to get lost in the Milky Way. So, but that's a pretty good picture. The door was left open. We were doing some other stuff inside the observatory and with messing around with telescopes. So we turned the lights on in there, which is kind of a no-no if you're trying to do photography. But, you heard John say I was complaining at him because he was out doing light painting with all this some nights. And I say, don't do that because people are trying to take pictures and he's shining lights around, which is, you don't usually want to do that at star parties or when you're even working to take photographs. So anyway, that's the one we did. We did two. So this was the first one. We caught both of them. And then, like I said, John took all of these nightscape shots. Then here's another one from slightly different angle, away from the observatory. You see, this is Jupiter again. So it's a little bit of a time exposure. Here's the Milky Way. You can it kind of loses Scorpius in there. I thought we'd be able to see it. It's funny that I may add some pictures tomorrow night. I was looking at some photographs that we had taken in 2018, and there's a very good nightscape shot of Scorpius that John took then. And it was, wherever he was and with the setting and everything, but it was, of course, he might have tinkered with it a bit. But really, you see the Scorpion. Scorpius is one of those constellations that looks like what it's supposed to be. It looks like a scorpion. So, and that's it. That's all the folks. So thank you for coming, and thank you folks for being online. Do we have any questions right at this point? You folks that did, remote folks, do you have any questions?
Thank you very much.
Nope. Okay. We'll do another one like tomorrow night. And like I said, I'll repeat some of the things. I'll probably show you Saturn again because that's worth seeing every time. And some of the other highlights, plus a few that you haven't seen. And like for instance, tomorrow night, I'm going to show you some binary stars that are real binaries. And I will also show you a couple of photographs of the Andromeda Galaxy. And
Can you show us that blue and yellow star, the binary?
Yeah, I'll probably show that again. I'll show that again. Yeah.
We can figure out the rotation.
Right. Well, not so much there. You'd have to, one of the things you can do is, John, if you do a long-term time exposure, you'll see these concentric circles all around the Polaris. It actually moves a little bit itself. But it's close enough. You can go out in the field to do the observing, and if you set your telescope as if it's exactly the North Star, and all you're doing is observing, looking, you won't be able to tell the difference. If you start doing time-lapse photography, when time exposure photography, you will see things that blur because it won't. Your stars won't be sharp.
Yeah.
Yeah. Okay, folks. All right. Thank you.
Thanks, Roy. See you tomorrow.
See you
Thank
tomorrow.
you. Bye.
Okay.
Have fun.
Stop the video. Okay. Robin, you're the host. Let's end the session. I can't end it.
Click stop share.
Okay, I just,
Right, and then there's your end button.
where?
Right there, it's red.
Oh, I see it.
Right here.
Okay.